Okay, often as engineers, we're interested in um, sort of the more practical aspects of the fluid flow. It's like so we would like to know things like how much power is it going to take to pump a certain amount of fluid from point A to point B through a certain length of pipe and stuff like that. And so we have to overcome two things essentially. We have to overcome any sort of gravitational uh, change. Like so if we're pumping water up a hill, that's going to have an effect, right? It's going to require more power to pump water uphill. The only other major effect, and what we're going to talk about in this lecture, is that there's actually a friction essentially a friction associated with pushing fluid through the pipe. So as you push fluid through the pipe, there's a shear stress that develops along the wall, and that shear stress essentially you have to overcome that by with additional pump power. Okay, um, for we can derive an exact solution for how much pump power is required in the case of a laminar flow in a circular pipe. Um, this is a very simplistic case, but it serves as sort of a jumping off point for more complicated cases. And so the velocity profile of laminar flow in a circular pipe is known exactly, and this is it. Okay, so it's 2 times the average velocity times this value here, which r is the radial um, dimension. You know what I mean? So we're dealing with cylindrical coordinates here because that makes sense. And then capital R is the actual inner radius of the pipe. All right, and so uh, we have this parabolic profile, and like I just said, there's going to be a pressure drop along the length of the pipe. So at this surface, as I drawn here, the pressure is P, and at this pressure, or at this surface, the pressure is P plus a little bit um, pressure P plus dP, which dP is going to wind up being negative. Um, so plus a small change in pressure, okay, and over a length of dx. Okay, so this is the x direction, and so this is a small distance dx, and the pressure changes by an amount dp. Okay, and so what we can do is we can do a force, like in a steady situation, we'll have a force balance where the force of pressure pushing the fluid along has got to be balanced by the friction force acting at the wall. So the area of this small cylindrical region that I have illustrated here is the surface area, the cylindrical area, is given by 2r or 2 pi r, which is just the circumference of a circle times the distance dx. All right. So that's the sort of the perimeter, not the perimeter, but the the surface area of the cylindrical portion, and then the surface area of the two circular portions are given by just pi r squared. Okay, and so the force due to pressure is just that area pi r squared times the change in pressure. So you have a force over here acting on a force over here. The net is going to be the change in pressure times the area that it's acting upon, and then the force acting on the cylindrical surface is just the 2 pi r dx, which is the area times the shear stress. Okay. And so this simplifies. Just cancel out the pi's, one of the r's. R dp dx is equal to 2 times the shear stress acting at the wall. All right. And like we talked about before, the shear stress acting at the wall is just the viscosity times the velocity gradient at the wall, evaluated at the wall. And so I can take this. This comes out to be I'll leave it to you to calculate the derivative of that and verify that the velocity gradient evaluated at the wall comes out to that quantity. And so dp dx where I just took this r to this side, so this is the shear stress, divide that by r, multiply it by 2, and so that's where this comes from. And so I can integrate from this dp dx from 0 to L okay, and I get so that would be, what this comes out to be is the P at point L minus P at x equals 0, i.e. dP, this is this will come out to be the delta P, is equal to the integral from 0 to L of this right here, and there's no x value right there, so rather than rewriting it, I'll just, this is all constant, comes out front. And evaluated at 0. So anyway, it simplifies to that. So delta P comes out to that value, where this is a negative. Yeah, so this is less than that. So this is a negative quantity. You follow what I'm saying? So this is like this is decrease. This is a decrease in pressure along the length. Oftentimes, like, we tend to deal in diameters, so I can express this in terms of the diameter simply by plugging r, d over 2 in for r. And so for laminar flow, the pressure drop has an exact solution, and this is it. So where L is the length of the pipe, D is the diameter, and mu is the viscosity, and V is the average velocity, okay? Now, what we'd like to do is take this expression and sort of use it as a jumping off point for more complicated flows. So what we do is we just basically rearrange this thing. And we write it like this. So we do this so that we can basically come up with a formula for this new thing we've evaluated here as F. Okay, so we want to rewrite the pressure drop in that form so that we can apply this same formula to a turbulent case with just some other means of calculating this value for F. For laminar flow, F just comes out to 64 divided by the Reynolds number. And take the definition of the Reynolds number, plug this value in for F, and you'll see that you wind up just recovering that. So why would we want to do that? We would want to do that because the F is some other complicated function of the velocity and things like that for turbulent flow. So for first of all, F is called the Darcy friction factor. Okay, that's what F is called. It's a dimensionless quantity, as you can tell, because it's just a number divided by another non-dimensional number. For turbulent flow, F is given by something called the Colebrook equation. And it's somewhat complicated. You'll notice that the square root of F is on both sides of the equation. All right. So how did you come about this? Well, you just measured it. So basically, you take this relationship through a process called non-dimensional analysis, which is really just rewriting standard equations in non-dimensional form in such a way that the reason you would want to do that is because what we would like to do is take this value. Maybe you do a bunch of experiments using 1/4-inch tube, but we'd like to extrapolate this up to 2-foot diameter water pipes, running under the sewer or running underneath the streets or something. We want to take situations evaluated at very small laboratory environment and extrapolate it up to very large scale, pumping oil from across the country sort of thing. And to do that, we cast everything in non-dimensional form. I'm gonna post another video as sort of an aside. You cast everything into a non-dimensional form, and then everything scales. In non-dimensional form, things scale much more easily. Okay? Not really much more easily, but it's easy to apply the scale in a non-dimensional form rather than in the dimensional form. And I'll get into more details later. But so bottom line is, we did someone, probably Colebrook, did a whole bunch of experiments and made a plot for the friction factor or something like that, and came up with this experimentally. Now there's a couple parameters in there we need to adjust. These are just numbers: 3.7, 2.51. Okay, those are just parameters that were tuned in the experiments. This is the log base 10. Okay, now epsilon is the surface roughness. Of the tube. And D is the diameter, of course, and then F is the Darcy friction factor. And so you notice that the square root of F is on both sides. You can't actually solve for the square root of F. You can't really solve for F from this equation. So it's what's called an implicit equation. So you have to maybe use an equation solver on your calculator or something, or you use what's called the Moody chart, where someone basically took all the solutions and plotted them. So for various epsilon over d ratios that come up the side here, relative roughness, epsilon over d, okay? So the roughness divided by the diameter. Different values for those, for that parameter, gives you these green lines, all right? So you come to your epsilon over d, whatever it happens to be, and then the Reynolds number is given across the bottom. So you follow the green line, say you're 0.0004. Maybe you follow that green line over to a Reynolds number of, say, 2 times 10 to the 5th. And then you come over and you read that Darcy friction factor F. Okay, so you enter at the relative roughness. You come over to your Reynolds number, and then on over to the Darcy friction factor on the left-hand side. You'll notice it even has the, so there's actually a lot of information on this chart. You have the formula for the pressure drop that we just went over. You have that Colebrook equation. And then you also have the transition from laminar to turbulent flow. All that stuff's illustrated on the top as a function of the Reynolds number, right? So at about 4,000, you see the turbulent flow beginning, and the transition between that and about 2,300. Okay, then you see this green line. You see this green line representing the equation 64 over the Reynolds number. Okay, so there's a lot of information on here. So if you get lost and you don't remember what the laminar transitional or turbulent flow is, you got that. So you got some relative roughnesses, or some roughness values for various materials for pipes. There's a lot of information on here. Okay, so now that we have the pressure drop associated with just fluid flow in a circular tube, we'd like to relate that back to the mechanical energy that we lost. Okay, so the lost mechanical energy has to be put back in order to sustain the flow, right? So we have to have a pump further, upstream of the flow, that's providing mechanical energy that then is dissipated over the course of the flow. Or I guess you could put it on the suction side. That tends to be a bad idea. But so the bottom line is we have to overcome this mechanical energy that's lost due to friction in the pipe. So if we have a pipe, first of all, there's no work interaction. So starting with the energy equation, we can tell straight away that there's no work interaction. We assume that the Z1 equals Z2. So what I'm saying here is the work. What we're going to calculate here is the work required to push fluid through a horizontal pipe. If you're pushing it uphill, Z1 and Z2 won't be zero, right? But all I'm going to be talking about here is a horizontal pipe, just to overcome the friction. All right. Now, something that's a little less obvious is that the average velocities have to be equal here and there, and that's just a simple relationship due to the mass, right? So the mass flow rate is going to be the density times the average times the area, I guess, times the average velocity. All right. And the mass flow rate at point 1 has to equal the mass flow rate at point 2, right? And we have a consistent diameter of pipe, so the area is going to remain constant. We're assuming that the densities are going to remain constant. So if densities remain constant and the areas remain constant and the mass flow rate is remaining constant, the average velocity must remain constant, right? So the average, and also the velocity profile is essentially constant. If all these parameters are remaining constant, the velocity profile is remaining constant, so these alpha values are going to remain constant. So this whole thing simplifies down to So the mechanical energy lost per unit mass is equal to these two, to the difference in pressures divided by the density. Okay. Now, what we're actually after is the total work required. Okay, so we have to remember back at the original when we were deriving this form of the energy equation. All these are energy per unit mass. What I need is energy per unit time. Okay, so I need to multiply all these by the mass flow rate. Okay, and so here I get so I guess this would be um, so mass flow rate times the energy lost per unit mass gives me the actual work lost. Okay, so this is actually going to be what the value that I'm after. Okay, so this is the mechanical work lost, i.e., the mechanical work that I have to replace in units of watts. Right up here, the values in parentheses has units, or everything up here has units of say joules per kilogram. Okay, everything in this, everything in the energy equation has units of joules per kilogram. If I multiply through the mass flow rate, I have total power. All right, so this is the amount of power that I need to replace. But if mass flow rate divided by the density, if you remember, mass flow rate is just the density times the volume flow rate, and so the the amount of work that I have to supply to the flow to maintain the flow is just the pressure drop times the volume flow rate. Okay. And then there's also this quantity that that is on the problem sets called head loss. And if you remember, we were able to recast the energy equation and the Bernoulli equation in terms of head, right? So it's really just the pressure. If you remember, the pressure head is given by the pressure head is just pressure over the density times gravity. So the head loss is just going to be the pressure drop divided by density divided by gravity. All right. It's just another way of stating the same thing, right? So we have pressure drop. Sometimes you'll hear the quantity given as head loss. Really the same thing, just two different ways of discussing it. I guess mainly because this might have more use in things like pumping water over long distances or something like that. How high could you pump the water? You could only pump the water as high as the total head. That's as high as it'll go. That's as far up as it'll go and come to a halt. So how much head loss did you drop by? You know, how much head was lost? How much elevation did you lose if you had to pump, say, a bunch of water up into a tower or something? How much shorter did your tower get by pumping it through a certain length of pipe? So, you know, take that for what it's worth.